Our problem will be discussing the topic of energy. The problem states that a frictionless roller coaster of mass 500 kilograms starts at rest from a height of 80 meters above the origin. What is the speed of the roller coaster as it goes over the top of a 50-meter loop? Using the speed you just found, what is the smallest radius that guarantees the acceleration of the roller coaster will be less than or equal to 3.5 Gs in order to meet the amusement park's safety regulations?
First, we will identify the given variable. The height of 80 meters is measured from the origin indicated by the blue line to the top of the hill where the roller coaster rests. The first part of the question is shown by point A, while the second part of the question is shown by part B. The speed is found at the top of the loop, shown with v subscript b. The red highlighted area represents the distance from the ground to the origin of the roller coaster, which should not be included in the calculations.
Potential energy is zero based on the location of the origin relative to the height of the object, not necessarily where the ground is. Another misconception about the height is that it should be measured in the vertical direction, because this is the direction in which gravity acts. A height measured in any non-vertical direction would be invalid, because gravity is not acting in that direction. The physics principles illustrated include the law of conservation of energy, as work done by forces that are part of a defined system do not change the system's total energy. Because the roller coaster is in motion, it therefore has translational kinetic energy. When the roller coaster's height off the ground changes during its path, the gravitational potential energy changes. The centripetal acceleration is considered in order to keep the roller coaster in circular motion.
The first step in solving this problem is to define the system. In this case, the system includes the Earth and the roller coaster. It is important to realize that gravity is a conservative force and that work done by conservative forces that are part of a defined system do not change the overall energy of the system. Because the Earth is defined as part of the system, gravity acts as an internal force and does not change the total energy of the system.
So the solution for part A, we must find the total energies of part A and B in order to solve the problem. Due to the law of conservation of energy, energy is neither lost nor gained, and thus the energies will be the same. The total energies from point A and point B will be equal to each other. At each point, there is a presence of both gravitational potential energy and translational kinetic energy. Before inserting any known values, we will isolate the variable that is being sought for, which is the speed as it goes over the top of the loop. Once the speed is isolated, we can go ahead and insert our known values. In this case, mass is negligible and does not have to be accounted for since all the masses will cancel out. Inserting all the known values, we find our speed at the top of the loop to be 24 meters per second.
To solve for part B, we are going to use the definition of centripetal acceleration. Once again, we will isolate the variable we are solving for, which is radius in this case. We are asked what the minimum value of the radius that is needed in order to meet the given value of acceleration at less than or equal to 3.5 Gs. Thus, we can set the centripetal acceleration as less than or equal to the velocity squared over the radius. With the known values of acceleration and velocity being 24 meters per second found from part A, we can go ahead and solve for the radius. Once calculated, the radius will be 16.8 meters.
The first misconception is that potential energy is zero based on the location of the origin relative to the height of the object, not necessarily where the ground is. Potential energy at the ground does not always equal zero. Alternatively, if we don't define potential energy as zero at the origin, the height used to calculate potential energy would be incorrect, thus resulting in an incorrect kinetic energy. Another misconception is that the height must be entirely in the vertical direction because this is the direction in which gravity acts. Alternatively, if height were measured in any non-vertical direction, using this height in the potential energy calculation would result in an incorrect kinetic energy value. Lastly, gravity is a conservative force, and work done by conservative forces that are part of a defined system don't change the system's total energy. Because the Earth is defined as part of the system, gravity is an internal force and does not change the total energy of the system. Alternatively, if the Earth is not defined as part of the system, then the work done by gravity changes the total energy of the system. This is because gravity will be an external force and there will be no potential energy due to gravity for the system.